So I'm gonna, did you push the button? Is it running?
Yeah.
Thank you. So I'm gonna review some of the really important things about complex variable theory, and then proceed from there. Although, if one of you has a question, we could start out with that instead. Yes.
I have a question about the midterm.
Yes.
Will it be open book?
Yes.
Okay, and what will it cover exactly? Because it's
let's see. I think that the homework assignments have been scheduled in such a way that you will have done homework only on the first 4 chapters. Is that right?
I think that's correct.
Okay, so it'll cover the first 4 chapters.
Okay.
And so there's a certain disconnect. We've already gone through chapter 5 in class, and we're going to get halfway through chapter 6 at least before the exam let's see, the exam is almost 2 weeks from now,
It
isn't it?
is 2 weeks from today.
Yeah, so there's a big disconnect between what's on the exam and what I'm lecturing about, which is unfortunate. But I don't know what to do about that. But yeah, open book. Okay, so I think maybe I'm going to do some of this stuff on the board. So let me do that. I want to remind you of these most important things about complex variable theory. And so first of all, the definition of a derivative, it's essentially the same thing. It's as an ordinary derivative, but the limit z prime to z has to exist no matter how you approach z, no matter how those z primes approach z. That's the distinctive thing about the function being differentiable. And so this then is, we say the function is differentiable, and if it's differentiable at all points in a disk, then it's a disk about some point z0, then we say it's analytic at z0, and if it's differentiable at all points inside the disk, then we say it's not only analytic at z0, but it's analytic in the disk. And the theorems that apply are in general true for functions that are analytic in a region that doesn't have any holes in it. And such a region, we say, is simply connected. So a piece of Swiss cheese is not simply connected, but a piece of American cheese is typically simply connected. Which reminds me of a saying somebody taught me, the early bird gets the worm, but the second mouse gets the cheese. Somewhat of a gruesome thing. Anyway, let's look at the Cauchy-Riemann conditions. So here we're saying that we imagine that we have a function f of x, and of course z is x plus iy, and so we can think of f of z as an f of x and y, or we can think of it as f of x plus iy. And of course, it's more useful to think of it as x plus iy. But you might be given a function of x and y, and then you'd ask yourself, is this an analytic function of z, namely x plus iy? Oh, that looks like an eta rather than a y. And so if you're given a function that's u of x and y plus iv of x and y, then you would ask yourself, is this an analytic function? And what you do is you'd apply this definition to the function, and what would that be? Well, it would be, in fact, let me use the notation that u sub x is partial u partial x. Then this would be u sub x plus I v sub x dx plus u sub y plus I v sub y dy. Well, that's the change in f, and so that's df, and that's would be f prime, it would be f prime of z, and the change in z is dx plus I dy. And now if f is analytic, then this equation has to be true for small x and small dx and small dy, no matter what the ratio of dx to dy is. So that's the idea of that you can approach in either direction. And so if we try the extreme case of dy equal to 0, we get u sub x plus I v sub x is equal to f prime of z times dx, and then I'm canceling well, all right, maybe I should do this in 2 steps. We get that equation. Then the other equation we get is that f prime of z I dy is the case where dx is equal to 0, so that's u sub y plus I v sub y dy. And so this, if we now cancel dx here and dy there, and note, and then divide by I, so that we have an I there and not there, then we have 2 expressions for f prime of z, and they say they say u sub x plus I v sub x is equal to minus I u sub y plus I v sub y. These are the Cauchy-Riemann conditions. The real part of this equation is u sub x equals v sub y, and the imaginary part is v sub x equals minus u sub y. So these are the Cauchy-Riemann conditions. This Riemann, by the way, is also the Riemann who invented differential geometry, on which, in other words, a way of analyzing shapes in multidimensional spaces, on which Einstein used to formulate general relativity. It's the same Riemann. Any questions about the Cauchy-Riemann conditions? They're quite important, and so what I want to do now is to repeat the derivation that I started at the end of the last hour of one of the really important theorems of complex variable theory, And the remarkable thing about complex variable theory is you have a simple definition, you have an immediate consequence, and then of these two results we can now derive a rather remarkable theorem, which is that the integral, the closed integral of an analytic function, in other words, an integral that goes back to where it started, as long as it's inside, it's totally inside a space in which the function f of z is analytic, then this vanishes. So this is Cauchy's integral theorem, and this is true as long as this is a simply connected region in which f is analytic, so no holes in particular, no holes here. So I'm going to do this for, in order to make the notation a little bit simpler, I'm going to, or simpler, I'm going to imagine a rectangle that starts at the origin and goes out a distance L in the x direction, goes up a distance h, and so this point is HL. This is in the, you can think of this as the complex z plane or the xy plane. X is going this way, y is going that way, and these are the x and y axes. And so I'm going to compute the integral of an analytic function this way, and then that way. And so the integral around this rectangle of f of z dz is then an integral around the rectangle of u of x and y plus I v of x and y dx plus I dy. So that's the nature of dz. It's the change in x plus I times the change in y. And we can separate this into then these four pieces here, and if we do, what we get is this, an integral 0 to L dx, just in the x direction, of u of x and 0 plus I v of x and 0, and y is equal to 0 because we're going along this line here, and then plus an integral 0 to h I dy of u of L and y plus I v of L and y. And this is L, x is equal to L because we're going up here, and we're going from 0 to h, integrating the y part. And then, I'm frankly always confused when things go backwards in integration, but what it amounts to is an overall minus sign. Or one can just write it explicitly. We're going from L to 0 of dx of u of x and h plus I v of x and h. So what we're saying is that that y is equal to h, but we're going that way on x. And then finally, an integral from h to 0 I dy of u of 0 and y plus I v of 0 and y. And x is 0 because we're going down this thing here. And so the useful thing then is to take the real and imaginary parts of this and see what they are. And the real part then of this integral over R of f of z dz, or RE, anyway, is is equal to, well, what is it? It's going to be that integral, but neglecting the I part, or the v part. It's going to be the v part of this integral, the u part of this integral, and the v part of that integral. And so it's going to be an integral 0 to L dx of u of x and 0 minus u of x and h, and then minus the integral 0 to h dy of v of L and y minus v of 0 and y. So that's the real part. We'll do the imaginary part later. Let's focus on the real part for a moment. In particular, this thing here, we can re-express as an integral. In other words, u of x and 0 minus u of x and h. This is just minus the integral from 0 to h dy of u sub y of x and y. So this is just, what you learned in calculus as freshman in college. Similarly, this thing here is also a simple integral. V of L and y minus v of 0 and y is just the integral from 0 to L dx, the x derivative of the integrated, integrated xy, and we're integrating x from 0 to L. So that means then that we can rewrite this as two double integrals. First one with a minus sign, 0 to L, that's this part, and then the difference in the u's brings in the minus sign, so we have dx there, integral 0 to h dy, and the minus sign is that minus sign, and what we've got is simply this, u sub y of x and y. And then this second integral here has, first of all, a minus sign, and it's integral 0 to h dy, and then it's this thing here, which is 0 to L dx, and so we've got v sub x of x and y. And so altogether, it's minus an integral 0 to L dx, 0 to h dy of u sub y of x and y plus v sub x of x and y. But now the sum of those two, uy vx, uy and vx, one is opposite the other, so they add to 0. So this thing is 0. So this is 0 by the Cauchy-Riemann conditions. We do the imaginary part, it works out in exactly the same way. Let me just first of all, the integral of f of z dz. The imaginary part of that, we'd have to go back here. And the imaginary part would be the v part of the first integral, the u part of the second, the v part of the third, and the u part of the fourth. And So in the so let's see, I guess I sort of skipped one of the, oh no, I didn't skip it. So let me write down what that is. The imaginary part then is an integral of 0 to L dx, v of x in 0 minus v of x in h plus integral 0 to h dy of u of L and y minus u of 0 and y. And now, once again, this is just an integral of the y derivative of v, and this is an integral of the x derivative of u, and in particular, v of x in 0 minus v of x in h is minus the integral 0 to h dy of x and y, and u of L and y minus u of 0 and y is an integral 0 to L dx of use of x and y. So putting these two in here, what we get is the imaginary part of the integral of f of z dz over the rectangle is minus the integral 0 to L dx, integral 0 to h dy, and in fact, if I do these together, it's minus v sub y of x and y plus u sub x and y. And now u sub x and v sub y, if we go back to the Cauchy-Riemann conditions, u sub x equals v of y, so their difference vanishes. And so this is just equal to 0. Okay, so this is very important. Does anybody have a question about it? I think basically this is all we need to conclude that if we have a region that's simply connected, no holes, and we have any closed contour, then the integral, we call the contour C, the integral, the closed contour integral of f of z dz is 0. And the way I think of this is something that I think 100 years ago would have been very strange, but now that we've had television for something like 70 years and computers with screens for maybe 40 years or 50 years, and laptops with nice screens, iPhones with nice screens. We're used to pixels. And in fact, what we like about the advances that Apple made maybe 10 years ago is that they made the pixels so small you couldn't see them anymore, and they called it the retina screen. But before the retina screen, you could see the pixels, and so you can imagine that you can take this simply connected region in which f is analytic, and you can tile it with rectangles. Of course, over here I said the rectangles had one corner at the origin, that obviously doesn't make any difference. You can go through the same thing with the rectangle anywhere in the xy plane. And it can be an arbitrary size and so forth. And so you can imagine that you cover this thing with rectangles, and in fact, some of them can be quite big. So here where I'm covering quite a bit of this thing, and I'm going out to say here, and then here I can sort of go to there, and eventually, with using smaller and smaller rectangles, we can get arbitrarily close to filling the whole interior of this region of analyticity, and in particular, we can do the same thing here. More importantly, in fact, we can cover the region inside the closed contour with rectangles, and like this and so forth. And now the integral of f of z around each rectangle is going to be 0. On the other hand, there are going to be the right side of this rectangle is an integral going up. The left side of this rectangle is an integral going down, and so those are going to cancel. The result is that what we've got then is a sum of integrals over rectangles. They all vanish, each of them vanishes, but also all the internal edges also vanish because they're always canceled by one going up and one going down. And as a result, what we're left with is these edges here doing the thing just sort of crudely. In other words, here we have a rectangle like that. We'd be left with this edge, we'd be left with an edge here, and so forth. And the edges that we'd be left with, after all the interior ones cancel, is exactly the integral along the contour. And so that has to be 0. Because the sum of all the sum of the integrals around each the integral around each rectangle is equal to 0. And the sum of all those is equal to 0. The interior ones cancel, so the exterior ones, which amount to this contour, cancel. So in my book, basically that proves Cauchy's integral theorem. And once again, I remind you that in order to apply it, you have to be able to say that f is analytic in a certain region, and that region can have no holes. So it's simply connected. An example that's actually will be useful to us later on is, imagine we just do an integral f of z dz around a tiny circle. And here I want to emphasize the circle is tiny. So its radius epsilon. So what we'll say is, since it's a very tiny circle, we can approximate, and of course, once again, it's f of z is analytic in a simply connected region, and circles inside the region. So we're talking about a region here in a tiny circle at some point, z0. So this is then f of z0 plus z minus z0 f prime of z0. And these points z are going to be z0 plus epsilon e to the I theta, where theta runs from 0 2 pi. So those are the points of a tiny circle that surrounds the point z0. And so dz, the only thing that varies then is going to be theta, is going to be I epsilon e to the I theta d theta. And so now if we just substitute in here, we have an integral 0 to 2 pi d theta, and then we have f of z0 plus, this is epsilon e to the I theta is that, f prime of z0, and dz is I epsilon, so I should have put I epsilon, and there's no room to write it, so I'm going to write e to the I theta out here. And now we can't just say epsilon's very small, so the whole thing's equal to 0. That's not the point here. Instead, it's that let's take epsilon to be finite, like 0.1 or something, or 0.01, but we're not sending it to 0. Instead, what we've got is we have an integral 0 to 2 pi e to the I theta d theta. And what is that? Well, that's e to the I theta evaluated at 0 and 2 pi divided by I. But e to the I theta, when theta is 2 pi, is 1. E to the I theta when theta equals 0 is 1. So this is 1 minus 1 over I, and that's 0. Similarly, we have an integral of e to the 2I theta, 2I theta d theta, and so this is 1 over 2I, e to the 2I theta evaluated between 0 and 2 pi, and this is again 1 minus 1 over 2 pi, 2I, and so that's 0. So these two integrals are, so this is of the form epsilon times 0 plus epsilon squared times 0. And it's 0 not because epsilon is small, but because 0 is 0. So that's another proof of Cauchy's integral theorem, but for a small contour. There's also this tiny square contour. Maybe I'll do this one by projection because it's less important. It's just another example of kind of the same thing. I hope we're, oh God. So let's see. All right, so we're at least in the right place. So okay, so a tiny square contour, and so what we've got is near z0, since this is a tiny square, it's again f of z0 plus f prime of z0 times z minus z0. And so this thing is, we can say that f of z0 is, or the integral of f of z has, first of all the integral of z0. Well, the integral of z0, of f of z0 around the square, we can factor out the constant f of z0, and then we just get the four sides of the square, epsilon, I epsilon, minus I epsilon, 0. And for the rest of it, we have the constant f prime of z0. Now we do z minus z0 integrated. And we imagine that z is, we imagine the points x and y. The point z equal to x plus iy is at the center of the square, so I1 is an integral x minus I epsilon over 2. Integrated, we get that. Up the right side of the square, we have this thing, epsilon over 2 plus iy times I dy. What we're doing there, you see, is z minus z0 times f prime. So this is z minus z0, and z is at epsilon over 2 plus I. Z is epsilon over 2 plus iy. We're integrating that, and we're subtracting x and z is this on the right-hand side, and this is actually z minus z0 because we subtract the x. Anyway, if we do all four integrations, you can see they cancel. So let me go back to a board now to illustrate something else that actually requires some visualization that I can do by writing on the board. Can't do that. So we imagine we again have a region that's simply connected in which f of z is analytic. And we have some point z1 and some point z2, and we integrate along contour 1, and we compare that with the integral along contour 2, and so one integral is along contour 1 dz f of z, and the other one is an integral along contour 2 of f of z dz. And both go from, well, maybe I should write it explicitly, from z1 to z2. But along contour 2 and along contour 1. So these are two different contours of this integration, so this way and that way. All right, but we can also consider, or in fact what we know is that the integral from z1 to z2 along c1 and then backwards along c2 to z2, that integral is 0. So 0 is the integral of f of z dz around the closed contour, and that integration is the integral z1 to z2 along c1 minus the integral from z1 to z2 along c2 of f of z dz. So since the total integral is, the closed integral is 0, these two guys have to be equal. So that means we have a general result, namely that if we have, again, a region of analyticity with no holes, and then any two contours that go from z1, from one point inside the region of analyticity to another point inside the region of analyticity, any two contours that do that are equal when you integrate f of z along them. So in other words, the integral, maybe I should write this down, the integral f of z dz from Z1 to Z2 depends only on, well, obviously f, the function, on the endpoints, and not upon the contour. The contour of integration. So the contour is, say, C. Contour C integration. So that's another important thing about complex variable theory. And what impresses me most about complex variable theory is it starts out with some very simple definitions and observations, and these simple definitions and observations imply everything else in the theory. And some of the chains of reasoning are long. We're going to skip the ones that are long, but many of the chains are actually very short. And I think that may be the secret reason why people love complex variable theory. And the reason is that it's so easy to understand. That may be why it fascinates people. Of course, as I said, you don't want to get too fascinated by it. So let me see whether I'm going to do the projection or whether I'm going to do I think I'm going to do this on the board also. So this is yet another way of understanding this, and that's the funny thing about complex variable theory. There's so many ways that are equivalent. So once again, we have a region, no holes, f of z is analytic. So let's consider the integral from w to z, dz of f of z, and we're going to call that big F of z and w. So we're going to define a new function. Now, the first thing to say is what we just learned, that f is independent of the contour. It depends upon z and w and f, but not upon the contour. As long as the contour, of course, stays in the region of analyticity of the function f, and we assume that region has no holes. Well, by elementary calculus, you can see that f prime of z and w, or rather I should say ddz, I'm just have w for completeness, that derivative is f of z. And that's just the standard thing of the integral of f of x prime dx prime up to the point x. The derivative of that is f of x. So, what that means then is that f of z dz is actually f prime of z and w dz, or it's equivalently df. So the function, the analytic function times dz is really the differential of another analytic function, which is its integral. That means then that the integral dz on a closed contour in here of f of z dz is equal to the integral dz, well, it's the integral of this. Don't look for this in the book, this is new. So I'm adding new stuff. I mean, it's not new in mathematics, but it's just not in the second edition. So we can write that as the integral of df of z. But df of z on a closed contour is just f of some point on the contour, z star, or z1 minus f of z1, which is 0. So this is another way of seeing that the integral of f of z around a closed contour is 0. It's 0 because f of z dz is df, d big F, where big F is defined this way. And the fact that you can make this definition relies on the fact that, you see, I'm saying here that f depends on z and w, not upon the contour. It's not upon the contour because f is analytic. Notice that in mechanics, you have a similar situation. You can say, if you have a force field, you can always define some v of r, say, as an integral up to r from some point, let us just take 0, of the force and maybe there's a minus sign there. I don't remember what the convention is in mechanics. You can do that, but in general, this depends upon the contour. It depends upon the contour unless the curl of f vanishes. If the curl of f is 0, this is independent of the contour. So this is the connection between the curl of f and analyticity, and it's within a minus sign. It's the same thing. It's the same idea. Let me give an example of this. The example is polynomials. The integral of z to the n dz. Well, z to the n is, or z to the n dz is just the integral of d z to the n plus 1 over n plus 1. Because dz to the n plus 1 is n plus 1 z to the n dz. On the other hand, this then is 1 over n plus 1 z1 to the n plus 1 minus z1 to the n plus 1, which is 0. So this is an example of this general result. And since z to the n integrated around a closed contour gives you 0, it follows that the integral of any polynomial z is 0. And you can then argue that pretty clearly any function that has a Taylor series expansion also integrates to 0. So these things are all sort of equivalent. Cauchy's integral formula. So let's do the infinitesimal form first. So we're going to do, we're going to integrate around a tiny circle. This is what I did over there. But instead of just having f of z dz, I'm going to have that divided by z minus z0. And once again, I'm assuming that all of this is inside a region of analyticity with no holes. And what is this? Well, it's going to be an integral 0 to 2 pi d theta times I epsilon EVI theta. So that's going to be dz. This is that, just as it was over there. F of z, on the other hand, is going to be f of z0 plus f prime of z0 times z minus z0, and z minus z0 is going to be epsilon e to the I theta. And we're going to be dividing by epsilon e to the I theta. Okay, so some things cancel. Namely, we have 0 to 2 pi. There's going to be an I and a d theta. The epsilon e to the I theta is going to cancel that. And so what we have is f of z0 plus f prime of z0 epsilon e to the I theta. Okay. Now, the integral of a constant d theta from 0 to 2 pi, of course, is just 2 pi times f of 0, f of z0. So this is 2 pi I f of z0. On the other hand, the integral of a constant times e to the I theta integrated from 0 to 2 pi, that's 0. We saw that 0 over there, under the clock. So that's all this is. So we get, for us, this is a miniature version of Cauchy's integral formula, namely that f of z0 is 1 over 2 pi I. You're going to see this fraction a million times. Integral of f of z dz over z minus z0, and this is a contour of radius epsilon. So when the limit epsilon goes to 0, we have this result exactly. Now what we're going to do is we're going to use what we learned about complex variable theory. You see, it's amazing the way everything sort of falls together. We're going to be doing, actually, let me get the picture so I get the directions right for this thing. So we imagine we have some point z0 inside this huge region of analyticity. And we're going to do a contour like this. By the way, the contours that we've been doing so far have all been counterclockwise, because we were saying that dz is I epsilon e to the I theta d theta, and so we're starting out theta equal to 0, theta equal to epsilon, and we go around like that until we get to 2 pi. So they're always counterclockwise. That's the convention. One could have chosen the opposite convention, but we almost always do things counterclockwise. This time, I'm perversely doing it clockwise. And then I'm going to go out on a straight line contour, and then a big contour here. So this is the huge contour. So again, everything inside a, let's see, something that's has no holes, I could call them no holy or profane. Should I call it a profane region? All right, I guess that's not as funny as I thought it might be. All right. So, I'm calling this the contour C prime. And what do we get? Well, first of all, and this is all inside a profane region of analyticity. Okay, so we integrate along here, around there, around there, around there, around there, around there, around there. Now, and what are we integrating? What we're integrating is around C prime, it's f of z dz over z minus z0. That's what we're integrating. Now, this function is analytic everywhere inside this profane region, apart from the point z0, because it's singular at z0. So everywhere else, analytic. So what we can do is we can gradually deform this thing so that it looks, for example, like this in one deformation. And then we can shrink these guys back and shrink these guys back until finally we have nothing more than an infinitesimal integration here, and that's going to be 0. So what we conclude then is that this is actually equal to 0. Now, what else can we say? Well, if we look at the next thing that we do is we imagine instead, we look at this from a different point of view and we bring these two lines together. Well, then they cancel. And so then we're left with what? We're left with an integral around like that. So this is then equal to an integral that is clockwise, a clockwise integral of f of z, z minus z0 dz. That's this small integral. This cancels, and then we have a big integral that's counterclockwise. And we call that integral c. It's a closed integral, f of z dz over z minus z0. But the whole thing is 0. This we've already worked out. This is equal to 2 pi I times f of z0 because it's the tiny integral. This is a miniature. This is an example of the miniature Cauchy integral theorem. But it's going backwards, so it's minus. So this is equal to minus 2 pi I f of z0 plus this integral. So that tells us that the integral along any counterclockwise contour of f of z dz over z minus z0 is equal to 2 pi I f of z0. This is a counterclockwise contour around z0, and once again the whole thing is in a profane region of analyticity. The way this is normally written is f of z0 is 1 over 2 pi I integral along the contour f of z dz z minus z0, and this is counterclockwise. Okay. This is the Cauchy integral formula. And it's one of these amazing things that it's rather easy to derive it from the most basic aspects of complex variable theory. But then once you have it, you can do a gazillion things with it. So that's why people love complex variable theory. As I said, physicists sometimes love it too much. But that's just the way So what can, just to show you how many things we can do with it, let's just write it slightly differently. Let's write it as f of z is 1 over 2 pi I integral f of z prime dz prime over z prime minus z. That'll be a little bit more convenient. Now let's compute the derivative of f of z. So the derivative would be f of, let us say, z plus epsilon, epsilon being some small complex number, minus f of z over epsilon. And so this would be 1 over 2 pi I integral f of z prime. And what we would have would be 1 over z prime minus z minus epsilon minus 1 over z prime minus z. So that's what we would have. Now here I've run out of blackboard, so I'm going to go to the projector because I've just run out of it. And so now we go to compute this. And what we have then is, all right, so I used a more general expression, dz here, and so instead of epsilon. Now we combine these two things together, and the part in the numerator just leaves us with just 1. And we get this expression here. We send dz going to 0 and we get this. So in other words, the derivative of an analytic function is 1 over 2 pi I, the integral, closed integral, counterclockwise, around the point z of f of z prime divided by z prime minus z squared. What happens up here is that there's a dz which cancels this dz, which is that dz, so that's what that is. You can do the same thing for the second derivative, and you find 2 over 2 pi I f of z prime over z prime minus z cubed. And then you extrapolate to the nth derivative, n factorial over 2 pi I integral dz prime f of z prime over z prime minus z to the n plus 1. So you have these remarkable formulas that are exact, that are independent of the contour as long as you stay within the region of analyticity, which has no holes, and you can choose any contour you want. You just have to go in a counterclockwise way, and you go around the thing once, you don't go around twice. So there are various applications. I'm going to skip them. I can do them if you want in the problem session next Wednesday. But this is so important, I just want to come back to it just in case one of you has a question. Remember, I still have candy for somebody who... Has anybody asked a question and not gotten candy today? Okay, so what about a question? Didn't you ask a question?
I asked him about the midterm, but I'm fine.
You don't want a candy? All right, well, pick one up on your way out if you want. So does anybody have a question about this? This is really remarkable. I imagine that Cauchy was absolutely amazed when he figured these things out and couldn't believe that it could be this simple. Couldn't believe that he had discovered something so simple and so important. And it is
Anyway, that's why I say people love complex variable theory. Now, I'm just reminding you of the Cauchy-Riemann conditions. And I'm also going to remind you what a harmonic function is. A harmonic function, just by definition, is one whose Laplacian vanishes. Now, if we're in two dimensions, as is appropriate for complex variable theory, that's uxx plus uyy equals 0, where uxx is just the second x derivative, uyy second y derivative. That's what a harmonic function is. But what we see here is that a function that's analytic has a real and imaginary part, each of which is harmonic. And why is that? Well, it follows from the Cauchy-Riemann conditions, which again is this business where you derive these things. That was the second thing that I derived in this chapter. And now we see it has all these implications. In particular, uxx, well, ux is vy, so uxx is vyx. And of course, that's also vxy. But vx is minus uy. And so we get that uxx is minus uyy. That means that the real part of any analytic function is harmonic. Similarly, vxx by the Cauchy-Riemann conditions is minus uyx, and that's minus uyy. So the imaginary part of any analytic function is also harmonic. So these are remarkable conditions. Now, harmonic functions can have saddle points, which is to say a point that is the maximum in one direction, but the minimum in another direction. But a harmonic function can't have a true minimum or a true maximum, because at a true maximum, the let's call it h, hxx would have to be positive, and hyy would have to be positive. Actually, that's at a minimum, isn't it? So at a minimum, a true minimum, hxx has to be positive, hyy has to be positive, but then it couldn't be harmonic. And similarly, at a local maximum, hxx would have to be negative and hyy would have to be negative, but that's impossible for a harmonic function. So this means that the real and imaginary parts of an analytic function, each of them has no minimum, no true minimum, and no true maximum. Now there are some electrostatic applications of that. The electrostatic potential is actually is a harmonic function in regions that are free of charge. That's because E, and we're talking electrostatic, so no time dependence. E is minus the gradient of potential, and by Gauss's law, the divergence of E is 0 if you have no charge density. So that means that the Laplacian of phi vanishes. And so that means that the electrostatic potential is harmonic in the more general sense of, is three-dimensionally harmonic. Namely that phi xx plus phi y plus phi zz is 0. So that means that in a region with no charge, the electrostatic potential can have no minima and no maxima. And that has a consequence known as Earnshaw's theorem, which is that you cannot trap a charged particle in an electrostatic potential. So if you have gone to a class in advanced optics or one of our physics colloquia, and you should go to all the physics colloquia. Most of them, in most of them you'll learn something, and they'll broaden your view of science. If you're sitting there and after 20 minutes you haven't learned anything, walk out. Nothing wrong with walking out. You send a message to the speaker that he's a lousy speaker, and he or she needs that message. Anyway, if you do go to advanced optics talks or lectures, what you'll find is that people have been trapping atoms, but they don't use electrostatic potentials. They use time-dependent electrodynamical fields. In particular, they use light field, the laser beams, and so forth. But it has to be time-dependent in order to have the atoms sitting in cups in space. The Cauchy-Riemann conditions also imply that the real and imaginary parts of harmonic functions are mutually perpendicular. So Ux, the gradient, two-dimensional gradient of U dotted into the two-dimensional gradient of V by the Cauchy-Riemann conditions vanishes. And we're out of time, so I guess I'll come back to this next Tuesday, but just quickly. So what it turns out is that you can use the real and the imaginary part to represent the electrostatic potential, and then the surfaces of constant U can be equipotential, and the surface of constant V can be the field lines or vice versa. And so all sorts of cute tricks that one can do, but of course you're stuck in 2 dimensions because the analytic function, oh, you have homework? Okay, we have homework here. All right, let me turn the lights on. Thank you. So, Pradeep, Lucas Webster, is that you?
No.
Lucas Webster's not.